Hello everyone, welcome back to my channel. We have seen how to design distribution network by using all those tools. Today we are going to see how to design clear water feeder main or gravity main by using WaterGEMs. So let's start the video. As you can see, I have already built a network. You can build your network by using model builder. So we will start. This is our MBR location and these are the host location. You can calculate clear water feeder main diameter by using economical dia Excel, but if you have multiple OSTs and bigger network, it's more time consuming in Excel than WaterGems. So we use WaterGems to save time. So we have 345-meter elevation. We will give another 20-meter, 345 plus 25, 370-meter staging, sorry, 25-meter staging. We will get 370 and 370.15, and here we will have 380. Okay, we have given the all the elevations to the MBR. Now we validate and see any problem there. So we get no problem. Negative pressure in the system, but we haven't given the demand set. You can give demand. You in this scenario you cannot give demand from load builder, because load builder gives you demand in whole network or selection set. So we will use demand center. You can go demand center and demand control center, click S, and here you will see all those junctions. Now we have to put demands in this area. So I have already prepared the demand. Okay. I will simply copy the demand and paste it here. So we have the demands, all the elevations, so we can run the network. Okay. Here we have the user notification that pressure goes below physically possible pressure, lowest physical possible pressure. So there are some points where we have negative pressures. Okay, here we will get everything and everywhere we have negative pressure. So we will go to the flexible pipe and check where we will get where is the problem. So you will see we have the diameters 57. We need to increase those diameters. We are using DI pipes, so we will change the materials. DI-K7. DI-K7 generally uses in gravity mains. In pumping mains we use DI-K9. We are using DI-K9. Our minimum dia is 100. So we will give 100. We have Eisen-Williams is for DI pipe is 140. We'll put 140 in this section. Now we have to give losses. We can provide minor losses by using user defined length. Click on value and tick the box. You will active this cell and copy all the length from here and paste it here. Then click on global edit, set in multiply by 1.1. It means it gives 10% losses, minor losses to the network. Okay, now our network is ready. We will run again. Here you can see the pressure is somehow increased, but we need positive pressure on the junction, so we will continue increasing pipe size. So head loss gradient uh, is 113. We need to decrease that head loss gradient. Okay, we will increase diameter of these four pipes in 150. Then try to run again. Then again change it to the 200. Here you can see the head loss gradient is in limit and velocity also is under control. So we will check the pressure again. Okay, run, and still some pressures are below positive level, some are going negative. You can either increase the staging height or increase the pipe size. We will see how much loss this pipe have. It's have 1.57 meter head loss, so we will just ignore that for now. Is a 4 meter, and here you can see head loss is 25 meter. Okay, we need to decrease that head loss to increase the pressure in these areas. Okay, how we can increase the increasing pipe size. Pipe on, this goes 200, this goes 150. Now we will see the pressure difference. Okay, pressure we have increased 15 meter, and in this OHT we have 5 meter, but in this OHT we still have minus 15. We will check the other OHTs. In this OHT we have 6. Minimum you need 3 residual head on the uh, FSL of the OHT. So these are not the GLs, these are the FSL of the OHTs. Okay, 3, 18. We will directly change from flex table, go and see. Here you will see this point. One point has 1 meter residual head and second point has minus 15 meter. So by increasing staging height, you want increase the you can increase the pressure in this OHT because the elevation difference is too high. Okay, we need to do something else to increase the pressure. We need to use pumps for this area. Okay, all the other areas are perfectly um, designed and pressurized. Okay, for this area we will use pumps. What we can do, create junction here. Okay. Now use reservoir. These are the localized sum. We have to uh, pump water from this reservoir to this OHT. So how it will work? The water will come through MBR to the reservoir. Then we will use pump from reservoir to pump to the OHTs. Okay, so we will give the GL here. GL simply something this 10 meter or okay, we have 1.65 meter pressure on the sump, so it is sufficient to provide water inside the sump. Now we have to use pump. You can go to the layout and use pump to the this point. Okay, we will give name to the pump 1 and reservoir to sump. Okay, now we have arrangement something like this. Water is coming from this point to reservoir and reservoir to OHT. Okay, we have to define the pump definition. You can go to the home. Here you will get pump definition. Okay, I will delete the existing pump and create new pump. Just rename the pump as pump 1 and choose standard from design point 1. Okay, now you have to give the flow and head. So first we need how much head we are required this point. First put the demand. You will get the demand here. You see 2.07 liter per second. You will add the demand here. Okay, then as well as in the pump definition as well. Provide 0.2.07 and I will just provide head 10 meters and close. Click on the pump and here you will see pump definition. Click on the drop down arrow and choose pump 1. So we have provide the pump definition to the pump and we have to provide GL to the reservoir. Okay, as well as pump. The elevation of pump should be lower than reservoir. Remember that. Provide 8. Now we will test again, validate and compute. Still we have negative pressure in the system. Here you will see the 10 meter head is not sufficient, so we will increase the head. Go to the pump definition, increase by 15 meter head. Okay, now run again. We have negative pressure here. So we will change 100 mm to 150 mm. Okay. Still showing negative pressure. Something is wrong. This 64, this 64 9. 14 meter. Okay. I only minus 14 meter. I have to minus 5 meter container height as well. It is the elevation of staging height plus 5 meter container. This is the FSL. Okay, I only minus subtract the staging height. So I have to minus 5 meter. So I just go to the 60. Okay, now we have perfect pressure on the all the OSTs. Okay, see all the OSTs are have the pressure. This is very easy way to solve the network. This is not very hard, but if you have multiple OSTs more than 50 or 100, so you will face many difficulties. So you have to give uh, these sums more than 5, 6, 7 times. Okay, or you have to use IPS intermediate station at this point or this point where you will not get the sufficient pressure. So this is for the ultimate year. You have to same design for uh, intermediate year as well. Okay, so I have made two scenarios for ultimate and intermediate year. You have to change uh, the demand for intermediate year as well. Go to the demand and I have these demands. I will put into the network and run the network. Pump definition is undefined, so we have to define pump definition as well. Go to the so this is the demand we have to put here 1.67 and pump definition as well. Create one pump 2 and put the demand here for intermediate here and give 10 meter of head. Now we will see the pressure difference. Pump definition undefined. So we have created pump, but we didn't define the pump definition. So we will go to the pump 2 and still we have invalid tank operation. Okay, we have to provide elevations. We have 345, 370 and 380. Sorry, 375. Okay. Now we will validate again. No problems and then run. Pressure is in negative. We have to increase pipe size again. Okay, you have to make all the changes here as well. 140 DIK7 and diameter 100. Okay, you can use or you have to use the 10% minor losses. So I will simply put 10% minor loss by using length. Okay, now run again. Nothing much of a difference. So here you will see the elevation is 0. Here elevation is 360. Here elevation 360. 359. 5. Always remember the pump should be lower elevation than reservoir. Now we will run again. This point have the right pressure, but we don't have pressure here, so we will increase the pipe size. Sometimes department ask for intermediate and ultimate both the years for better understanding of current scenario. Okay, we have to use same dias as ultimate year because dia bond changes with the intermediate and ultimate years. So I will simply go to the pipe and use short ascending to the pipe label and copy all the diameter. Then go to the intermediate here, repeat the same thing and paste all the diameters. Here you will see and click on compute. We will check the junctions for intermediate here. We have minimum of 3.81. So all the junctions and OST junctions are well pressurized. So we have completed the network with having all the pressures and by using one pump and one sump. So you can use this method to solve your gravity main or feeder main. Okay, so that's it for now. If you have any queries or questions, you can ask me, or you want to know about the scenarios and alternatives, you can see my other videos. I will provide the link in the description. So subscribe the channel to not miss the any of my other videos. Thank you for watching.